All right, welcome everybody to week 4, day 2. Lots of extra credit opportunities coming up. Just check Canvas, keep on top of those things. Let's talk a little bit about Class Playground. The biggest problem that I've seen with the Class Playground assignment is, for one, people just not knowing what a copy constructor is. And I did go over it last time. It gets called when you do this. When you pass something by value, it creates a new map and copies the old map into the new map. That's what call by value means. Call by value means you clone the object. Whereas when you pass it by const reference, it's the original object, no copy is made. That's why we don't like call by value for large things like these large arrays and stuff like that when we don't need them. So, a couple things I noticed on this. This one's been fixed, but a lot of people are using greater than size. So like if you had a 10 by 10 array, it would only bounds check properly if it was at 11. But remember, 10 is out of bounds too. If you have a 10 by 10 array, they go from 0 to 9 and 0 to 9. So 10 is out. And so I've seen a lot of off by 1 errors caused by people using greater than rather than greater than or equal to. Remember, the pattern for bounds checking is if x is less than 0 or x is greater than or equal to size, or y is less than 0 or y is greater than or equal to size. Now the reason why we don't have the less than zeros here is because we're using unsigned integers. Unsigned integers were made for this reason, specifically so you don't have to check for less than 0. So for this assignment, all you needed were the greater than or equal to ones. But a lot of students used greater than instead and had off by 1 errors as the result of that. A lot of people also didn't understand like the starter code. The starter code here is making, if you have a size of 10, this makes a 10 by 10 array, not a size 10 array. It makes a 10 by 10 array. Size is one of the lengths of the square, not the total amount of elements. And you have to use a for loop to loop over the 10 by 10 or 100 by 100 array. So the equals operator and the copy constructor are very similar. The difference being an assignment operator, you could say like A equals B. So A might exist already. So you have to delete the old array and allocate a new array. Whereas with a copy constructor, you just knew the new array. Now, for this one, he's not doing that because he's assuming the right-hand side, when you say A equals B, that B is going to have the same number of elements as A, which is dangerous. This code is, I would not consider this correct. Because if you have a 100 by 100 array on the right-hand side, you have a 10 by 10 array on the left-hand side, it's going to try copying, right, there's a mismatch. And so this for loop is either going to copy too few or it's going to copy too many. So this probably saves it because this does bounds checking. But honestly, this code should check to make sure that both the left and the right-hand side have the same 10 by 10, 20 by 20, whatever size. Now, the copy constructor, most people forgot this. When you copy from one vector to another vector, you have to copy everything, not just the data. You have to copy the size as well. Like, how many elements do I have? What's my capacity? You have to copy every element out of it. And so a lot of people forgot this part right here. And so their arrays were like 100 by 100 when they should be 10 by 10. And they kept getting these arrays that were too big. And some of them were trying to do this, like they were trying to say size is equal to, kp.size or whatever. And that didn't work. And the reason why it didn't work is because size is a constant. And the only time, I've mentioned this before, but the only time, but people don't remember it until it actually bites them, right? You can't do this because it's a constant, but you could do this. The only time you can ever set a constant within a class is in the initializer list, like this. That's why we use initializer lists, so that it works with const stuff. Also, a lot of static analysis tools work better when you do things in initializer lists rather than putting in the function body of the constructor. Can you explain what typedef is? Yeah, so typedef is making a new type called data type that is int. It's essentially an alias. So every time you see the word data type appear, that means integer. Now the reason why we do that is because if we want to make this a map of floats instead of events, we do that. And now everywhere down in our code where data type appears, data type appears, data type appears, it's now a float instead of an int. There's a arguably better way of doing this that we're going to learn in a few weeks called templating. But this is basically just doing a search and replace. Every time the word data type appears, it puts int there. And yeah, so the copy constructor and the equals operator both have to loop, and they have to copy every element from the right-hand side into the left-hand side. A lot of people just did this. Array is equal to right-hand side dot array, and that's wrong. If you do that, that's what we're trying to avoid, right? The right-hand side is a pointer at an array. Now the left-hand side is pointing at the same array. If you read and write to one, you read and write to the other one, it's wrong. You need to make a copy of it. And when one goes away, it deletes it. And when the other one goes away, it double deletes it. And then that causes a seg fault. So don't do this. This is wrong. Okay. This code here is mostly correct. And here you see it's doing a square array of 10 by 10. And then it loops over the whole thing and grabs the value from the right-hand side and puts it in the left-hand side. You don't have to use get and set like that. You can just copy the data directly, but that's fine. Okay, so that was Class Playground. It was designed to give you some experience working with copy constructors, assignment operators, and operators. The operators are going to come up again on the current assignment. So the current assignment is for you guys to work on something called imaginary numbers. So imaginary homework. You're going to type in something like 1 plus 1i plus 2 plus 2i is 3 plus 3i. 0 plus 1i times 0 plus 1i. What is I times I? You guys remember your algebra, your imaginary numbers? What is I times I? -1. Correct. So we get -1 plus 0i. So it's -1. Okay? So 2i times 2i is -4. Okay? So this is what you're going to be working on. So you're going to be creating a couple classes. One that's an imaginary class, and you have to make all of these operators work. Plus, minus, multiply. And you see there's two multiplies. One is if you multiply an imaginary times an int, and the other one is if you multiply this one here, an imaginary times an int. And the other one is if you multiply an imaginary times an imaginary. Multiply two imaginaries together, you get an int. And if you multiply like I times 5, you get an imaginary, 5i. And so all of the functions you need are there. And you're going to implement them in what's called an implementation file. Some of these are done for you. And some of them are not. And so you need to pretend you didn't see that. Those were the answers. I am in the reference directory. Let's move into the not engineering.cc. Some of them are done for you. Some of them are not. There we go. Yeah, get out the Men in Black eye flasher thing. That's funny. So hopefully you'll be able to figure those out. Like, if I give you the minus operator, you should be able to do plus. You know what I mean? So for this assignment, you're going to get, well, there's plus. Okay. So there's plus, and there is minus done. You need to do multiply. I don't think there's a divide. You need to make a default constructor. You need to make a one parameter constructor. You need to make a getter. You need to make a setter. This is more practice making classes. So this is week 4. And I'm still essentially not on data structures yet. We're still just learning proper class design because I've been looking at the grades coming in on the homework assignments, and I'm like, nope, we're going to do more practice on it. And I hope you guys appreciate that. I'm going to keep going over this until you guys get it. Okay? So learning how to make a class, learning how to make operators, learning how to make constructors. The beatings will continue until morale improves, right? So what we have here, and our topic for today is actually what's going on here. So if I type make clean, you can see there's actually multiple .cc files. And so a lot of students are like, wait, there's 3 .cc files. Do you need 3 different mains? No. This is your first homework assignment where we've actually split the project into multiple source code files. This is very common, by the way, in computer science. Everything we've done in 40 and 41 at most has been a couple hundred lines of code. Who cares, right? Like, if I go up to like my, I don't know, 3D animation code, word count it, it's 300 lines of code, and it generates, Z-buffered, barocentric coordinate, animated, colored triangles, 300 lines of code, So, color's kind of cool now, I don't know. But if you're talking about like Windows, right? Like Windows 95 was like 1 million lines of code, and I'm sure it's much more now. How many lines of code? Now, lines of code isn't a good measure of like how complicated a program is. 50 million. All right, cool. But it's certainly a measure of how fast it compiles, right? Because the more lines of code you have, the more work the compiler has to do, right? It has just more stuff to go through. If we're going to look at like the Quake source code, like the Quake client, word count, all the files in here. So the Quake client was 100,000 lines of code. That's a full 3D game engine, 100,000 lines of code. Not too bad. Some of the stuff isn't even source code, like some of it's like a bitmap file and stuff. Let's say about 100,000 lines of code, right? So the server, $20,000 lines of code for the Quake server. Surprisingly small, right? Surprisingly small. And I think there's probably a header directory somewhere. Maybe not. Now the game code is actually in a separate directory. And here is what I'm most famous for online, which is custom TF. And my game code is 100,000 lines of code. So this is the Team Fortress source code heavily modified. So not all that is mine, right? In fact, I've probably deleted as many lines as I've added. I've deleted out of Team Fortress and added to Team Fortress. So who knows how many total lines are changed on it. But yeah, that's the game code. So you have 100,000 for the client, 100,000 for the game code that makes the rocket launcher shoot rockets and things like that, and 20,000 on the server. So it takes a while to build. Okay, so when you are doing imaginary homework, it's not going to take long to build it, but I'm teaching you guys how to set up projects so that when you have 1,000 different source code files, you don't have to recompile the entire thing every time you make a change. You change a float to a double, and then you have to sit there and wait 10 hours for it to rebuild 50 million lines of code in Windows 11, right? So if you that's how long it takes to do a full rebuild on Imaginary. It's not long. the goal of this is to teach you how separate compilation works. Okay? And so the way separate compilation works is each one of these .cc files is going to have source code in it. The header files don't have any source code in it, not like implementation source code. It just has what are called like function declarations and things like that. Like, hey, a function exists. Like when you look at imaginary.h again, you can see it just says, hey, there's a function called getCoef. Notice that it doesn't actually have the code saying return coef, right? It's just semicolon right there. This is something called a function prototype or a declaration. And it just says a function by that name exists. The implementation details for getCoef are found in imaginary.cc. And so down here, you're going to write return coef in it. And this imaginary : thing here means we are changing the getCoef function. We're defining the getCoef function for the imaginary class. And so you're saying, inside of the imaginary class, here is the implementation details of the getCoef function. And this split between a header file and an implementation file is very important because the header files are quite small, all things considered. And so what you can do is you can just, .h stands for header. And so what you can do is you can have, let me just show you something like this, then main.cc. Let's start over from scratch. Okay. So will this code compile? I'll explain what .o means in a second. Will this code compile? Yes. What is this foo person here? Is there a function called foo? No. So this code will not compile. It's like, I have never met this man in my life, right? But what you can do is you can promise, like, hey, there's a function called foo that returns a float that exists. Notice no curly boys here, just a semicolon. And so this is something called a function declaration. I promise you, bro, this function exists somewhere. And it looks like this. So with this, it's enough for C++ to compile this code. Note that I'm not getting any compiler errors here, right? Because I've told C++ a function named foo exists. It returns a float. That's enough for it to know what to do with it. And it knows it doesn't take any parameters. All right, cool. So if this, however, was a void function, then it can say like, no, this doesn't work. You cannot see out a void. Do you guys understand? So just by knowing what's called the signature of the function, this is called a function signature. Function signature is a return type, function name, and parameter list. That's enough for it to go on, okay? So I could say this thing takes an int and a double, and you don't even need to give it parameter names there. And so now, look, it knows this doesn't work. So it has no idea who's written this code, where it is. All it needs to know is the signature because it needs to know how it fits into my code here in main. And because I did not provide any parameters to it, it knows this is wrong. And so if I put in here a 10 and a 20.5, let's say, now it's happy. Okay. Will this code compile? I'm not seeing any compiler errors on it. Will this code compile? Does foo actually exist anywhere? Have I written it? So it's a bit of a trick question. Everybody's saying no. It's a trick question because yes, it actually will compile. Watch. G++ -c stands for compile, but don't go on. Main.cc. Compiles just fine. So, Sally, to answer your question, what is a .o file? A .o file is the compiled version of your source code. So we had our source code here in main.cc, and now it is compiled into this thing called main.o. It is the compiled version of the code. It's not an executable though. I can't run it because there's a step that takes place after the compilation step that most of you guys haven't heard of called the linker step. And the linker step is where you take all of your functions, and some of your functions call other functions, and some of those functions call other functions. And what the linker does is it takes the standard library and your .o files and it puts them all together. It says, okay, A is calling B and B is calling C, but I can't find C. Linker error. And so if we try compiling this code and linking it, this is actually going to link it together. We're going to get a linker error. This is not a compiler error. This is a linker error. That's why I said it was a trick question. Because you can't build an a.out out of it because foo doesn't exist. We pinky swore that foo existed and we lied to the computer, and now it gets its revenge. It's saying, I don't know how to build this. I can't make an executable because you never actually gave me foo. Where is foo? I don't know where foo is. And so LD is the name of the linker, and it's saying, main, you told me, you promised me that there was a function named foo that takes an int and a double, and I can't find it. Undefined reference, I can't find it. Okay. So if I make a separate file called bob.cc, and I can make inside of here a function called foo int x double y, and it could like, I don't know, return x plus 10 minus y, I don't know, something, you do something. Now, if I compile Bob, and again, I'm using -c. -c means compile, or partially compile, we call it sometimes. This doesn't build an executable. This does not build a.out. It just makes bob.o. And so bob.o exists now. Okay, so we now have partially compiled version of main and a partially compiled version of Bob. And if I put these two things together, have I completed the jigsaw puzzle? Has every function in main, does it exist now? If I take this and I take this, can I put them together to make an actual executable? Hazelton says no. Well, he's a graduate. You should listen to him. Actually, Barbarossa, you're right. Okay. So, yeah, this is actually all you need. So if you compile these, if you take main.o and bob.o, it gives you an executable, and everything works. Okay. So bob.o only contains one function called foo. If you look at main, you can see it has a call to foo here, but it's undefined. So main is trying to call foo. It doesn't know where it is. What the linker does, it says, okay, you're trying to call foo. Where is it? And then it finds it over here in Bob. Okay, cool. And so you have to provide it the name of all the .o files in order for it to solve the puzzle and put it all together. And then the linker builds the executable out of it. Oh, and this is like a CSI 45 thing, but it shows you the list of functions that are in a .o file. Main exists here, but foo does not. It's calling foo, but foo does not actually exist here. And it's telling you like what offset main is at. Main is at offset 0. If we made a function called bar, it returns 42. And we partially compiled main again. The address will never be null. Function call, thank you very much. Thank you, warning. Always pay attention to your warnings. Okay. And then if we look at main.o now under name, nm is name. It's just a list of the names, basically, if you want to think of it that way. You can see that bar is defined here, and foo is not. And so it just shows you which functions are in a .o file, which ones are not. It's something that'll matter in CSI 45. It's not something that you need to know right now. Okay, so yeah, if you just try compiling main.cc on its own, you get a linker error because it can't find foo. But you could, of course, do this main.cc and bob.cc at the same time, and then it works. But you don't want to do this because then you're going to be recompiling all 50 million lines all at once. So with that under our belt, any questions about this before I delete them? Nope. All right, cool. Remove all of the .o files as well. So let's hop back into imaginary homework. So what you see now is make clean, cleans everything up. It deletes all the .o files, deletes the a.out. You can see that we've got 3 different .cc files. And when we type make figures out what we need. It figures out what needs to be built. And make is controlled by something called a makefile. So capital M makefile right there. And the format of this is basically saying, this is what we want to build, colon, these are the things that we need to build it. So in order to build a.out, we have to have main.o, complex.o, and imaginary.o. And the way that we build this out of those 3 things is this line of code right here. Okay, well, that's cool. But how do we get main.o? Well, I'm glad you asked. Main.o depends on main.cc and complex.h. Why does it depend on complex.h? Because main.cc includes complex.h. So if complex.h changes, then we have to recompile main.cc. And so if main.cc changes, it rebuilds that. If complex.h changes, it rebuilds that. So how do we get to here from these guys? We do a partial compilation, G++-C. And what about complex.o? How do we make that? Well, that one depends on 3 things. And we get there from there by doing that. What about an imaginary.o? Imaginary.o depends on these 2 things. And that's how we build it. So when we hit build, or make, it figures out exactly what needs to be done, and it does those commands. Now, if I type make again, I don't need to do anything. Why? Because everything's been built. So let me show you the power of Makefile now. I come into main.cc. I cout hello world. How many of these things need to change? Do I have to do a full rebuild? All I've changed was main.cc. How many of these CC files have to be recompiled? 1, 2, or 3? Just 1. Pretty much always. If you edit a .cc file, none of the .cc files depend on each other. That's why you have header files. The header files are kind of like how they communicate to each other, right? If a header file changes, oftentimes you have to rebuild your entire project, which is a pain in the ass. Like, I was once having to fix problems in my header file, and every time I changed anything, it would take an hour to rebuild the entire project. And then I was like, oh, shoot, I made it an int, not a float. And then I changed it to a float, and then hit make, and then it would take an hour. And then I'm like, oh, shoot, it was supposed to be double. You change it to a double, and then it's another hour. And so I'm like, I worked a full day, and wrote like 5 lines of code, because every time I changed something, it triggered a full rebuild. And then I had to test the code. I'm like, oh, wait, that's not right either. Oh, so frustrating. But yeah, just 1. So if I rebuild it, it only recompiles main.cc. That goes from main.cc to main.o. It rebuilds. It saves the compilation. Do you guys understand? So it's saving the result of the compilation into a .o file with the same name. Does that make sense to you guys? It does this normally. You just don't see it. So if you were to like make clean, and you were to like G++ star.cc, it actually makes .o files. But because you didn't use the -c command, it deletes them. So by default, it makes a .o file, links it together, and then deletes all the .o files. So if you want to preserve them, you have to use -c to save the results of your compilation. And then anytime you edit a file, when you recompile it, it only recompiles that 1 file. Or if you touch 2 files, Touch, by the way, just changes the timestamp on a file. Imaginary.cc. So it's pretending like I'm editing it, right? So I don't actually have to go in there and add like hello world or something, right? So if I touch 2 files, then it compiles those 2 files and nothing else. So this allows you to actually get work done. When you're on a large project, you do not have to recompile 50 million lines of code every time you change 1 line. Instead, you only have to recompile the file you're in, which is nice. You recompile that 1 file, and then it relinks, and you're good. Okay? It's just like how you don't have to recompile your code if you just change parameters on Unreal. Yeah. Because it's already compiled the shaders. It's just the parameters that go into it that change. How to write a Makefile. Glad you asked. I have a presentation on the subject. So, in the previous class, I was talking about touch. And so basically, Makefile works on timestamps, right? So if the timestamp changes, so here is A.out. It was built on February 1st at 3:16. If any of these things ever have a timestamp later than this, then it's like, oh, that's a new change, and then it rebuilds. And all touch does is it changes the timestamp. So you can see I just touched complex.h. So its timestamp is now later than that of the build. And so everything that depends on complex.h is now going to get rebuilt, which is these 2 guys. Okay. So I've got a presentation. So if you guys want to learn how to do separate compilation, it's lecture 7. And you guys know how hashtag include works, right? Like when you include something, what it's doing is that it's copying and pasting the entire file into your file. And this doesn't look like a lot of code, right? It's like 27 lines of code. It's actually 53,000 lines of code. 54, basically, if we round up. It's 54,000 lines of code. You're like, what? There's not 54,000 lines of code on the screen. There's only 26 now. Yeah. What's happening is that it's copying and pasting that entire header file there. And it's copying and pasting that entire header file there. And it's copying and pasting the entire imaginary.h there. And if you want to look at it, you can use the -e compile flag, and it will show you everything that is now inside of your source code. I don't know why you'd want to look at it, but there you go. That's what's in your source code. So in order to stop something from being included multiple times, like we did this 5 times, that would be bad, right? Like maybe copying and pasting it 5 times. It's also going to be violating the one definition rule, the ODR. The ODR says a class can only be defined once. So what we do is we put hashtag pragma once at the top of a file. And what that does is it stops a header from being included multiple times. And basically, best practice, put pragma once, hashtag pragma once at the top of every file. Every header file. .cc files don't need it because you do not include a .cc file. .cc files are implementation files where your code is. Header files are what you include. Implementation files are where you actually write the code. You guys understand? It's an important difference. And also, a lot of students think they have to put like a main inside of every .cc file. No. You should only have one main. Like if you try putting like a second main into here, int main, and you try building it, you're going to get a redefinition of main. Okay? So you've got one main inside of main.o, and you got one main inside of imaginary.o, and all hell breaks loose. Do not make multiple mains. Main goes in main.cc. Okay. Cinda, I've been writing thousands of lines of code now. You didn't know. Hashtag or bracket no return. So bracket is a compiler attribute that just tells the compiler that a function no return. It tells you that this function actually never returns, and you don't have to do it. It doesn't actually matter, like for any purpose you care about. like for a die function, when it exits like that, that tells C++ this function never actually returns. So don't worry about anything after you call this function, because this function never returns. It's like the end of your program. If you don't have it, you will not notice a single thing different. So you don't need to worry about it. How about that? It's good coding practice to put it there. It literally does not matter. So what does matter is hashtag pragma once. Because if you don't have that and something gets included multiple times, including transitively, right? Like if main.cc includes imaginary.h and main.cc includes complex.h and complex.h includes imaginary.h, now it's been included twice. So even if you're not dumb enough to like copy paste, like, look at me, look at how smart I am. Even if you're not dumb enough to do that, sometimes you include a file that includes the same file. Like a lot of people include IOStream, right? And so if you include 3 people and they all include IOStream, you want damn well sure that IOStream has hashtag pragma once on it. Now, you'll see some people object to the use of pragma once because it's not in the standard or whatever, but every compiler implements it, so that's my advice. I can show you the alternate way that's the correct way if you want. If def imaginary h, if not defined imaginary h. Yeah, I know. Define imaginary h, and then at the bottom, you have to have a hashtag indif. And every one of your files has to have its own unique token. If you copy and paste any of these by accident, it breaks all of your code. It's 3 lines of code. You have to remember to have something at the bottom of the header file and at the top. I actually don't like it. I actually don't like header guards like that. I actually just like hashtag pragma once. It does what header guards are supposed to do, but does it better. And the only downside to pragma once, these two things are doing the exact same thing, by the way. It stops it from being included multiple times. There's no difference between these 3 lines of code here and this 1 line of code here, except the header guards are a lot more likely you're going to screw them because copy-paste errors happen. And if you copy-paste error something, then you can't include those 2 files at the same time. It breaks everything. So I just don't use compiler guards anymore. I use that. So just 1 line, put it at the top of every .h file, good to go. All right, so does that only apply when there's an exit? Yeah, you only use no return if your code doesn't return. And the only way that your code can not return is if it dies. Die. Okay, so coming back here. Yeah, thank you, Bedencourt. Perfect. So yeah, C++ is dumb when you include the same header twice. Java is actually a lot more sensible about it. But okay. So yeah, so what you're going to do for this project is you're going to have multiple .cc files, and a lot of times they'll include the same header files. That's how they can kind of communicate with each other and stuff. But you don't want to build your code using g++ star.cc. That's slow and inefficient. Instead, it's funny. Am I laughing at my own humor? Yeah. Look, if dads don't laugh at dad jokes, who's going to laugh at them? So, killing myself here. So yeah, we're going to talk about where programs come from now. You're ready for this. You're old enough now, you can understand where programs come from. It's actually more complicated than what you think. Because when you type something like G++ main.cc in your normal projects or whatever, G++ is actually a front end. It's actually, it's sort of like a veil hiding different programs inside of it. So there's actually 4 different programs that run, probably more, but at least 4 big ones that run when you do G++ main.cc. It first runs the preprocessor. The preprocessor does the hashtag include stuff, which copies and pastes and does defines and things like that. It does a preprocessor first. You can do hashtag define to make constants, like in C, basically. The ones and the zeros. Yeah, it's like the birds and the bees. The ones and the zeros. How to compile a program. Step 2. Then the compiler runs. The compiler is the hardest step, especially time-wise, right? Like as it goes through the code, it keeps track of every variable it's seen. It keeps track of every function it's seen. It does type checking on basically everything. If you try assigning from a string to an integer, it goes, no, not allowed. Hey, I've never heard of you, compiler error. That function has the wrong number of parameters, compiler error. You're telling me that it is, G++ is actually 4 goblins in a trench coat. Yeah. So that's why you for declare things, right? If you ever call a function that it's never heard of, it's like, nope, compiler error. And so when you for declare something, it writes it down on a piece of paper. Like, okay, there's a function called add. It returns an int, and it takes 2 instance parameters. All right, got it. And then the next time you call it, even if it has never seen the definition for it, it knows that function exists somewhere. You pinky swore, right? So, it's fine. It'll pass the compile step. Now, after that, you get the it generates the object files. It always does it. Normally, just deletes them for you. It'll make all these .o files. And then after that, it runs the linker. There's also the assembler in there somewhere. The assembler you'll worry about in CSI 45. For now, don't worry about the assembler. The assembler's name is as. What code is used for the compiler? C++. C++. The compiler works on C++. The preprocessor only looks at lines that begin with hashtag. The preprocessor ignores basically every other line. And the preprocessor produces a C++ source code file, 53,000 lines long. The compiler then goes through all 53,000 lines and turns it into assembly. The assembler, whose name is as, generates the object file. The linker then LD puts the object files together into an executable, and voila, you have an executable named a.out. Okay. So the format for Makefiles is this. Okay. So there's alternatives to using Makefiles. Who compiles the compiler? The compiler does. You compile the compiler using the compiler. Seriously, the C++ compiler is written in C++. You make the next version of the compiler using the previous version of the compiler. What you're asking, though, really is the bootstrap problem. Like, if you have a brand new system that has no compiler on it, how do you get it going? And the answer is you have to bootstrap using assembly. Assembly is the built-in programming language for a CPU. And assembly looks like a foreign language to most of you guys because you haven't learned assembly yet. It's actually not hard. Betancourt's tag right now is he loves assembly. And ARM assembly is actually a lot of fun. It's actually pretty easy to learn. But that's what you start with. You start with assembly, you build a very simple compiler, and then using the simple compiler, you make a more complicated compiler, and you bootstrap yourself up that way. Nobody writes a compiler in all assembly. It's not done. No. But yeah, compilers are written in C++. And there's tools that like help you build compilers as well. Okay, so let's learn the Makefile format. So the Makefile file format is a target. That is the thing that's going to be built. Colon, a list of dependencies separated by spaces. So looks like this. So that is the thing that's going to get built. And these are the things that it needs in order to be built. So target, dependencies. Everybody type on chat, target, dependencies. Roller Coaster Tycoon was indeed built all in assembly. Widely regarded as an act of a wild genius, right? Like, nobody writes games all in assembly. Like, I saw somebody at Cambridge write all of chess, including the 3D graphics and AI, all in assembly. And I was just like, it's pretty, like, I wouldn't want to do that. Pokemon games, yeah. Target, dependencies, good. And then the next line has a tab. Okay, that is a tab character. That is not a space. That's not a space. That is a tab. Okay, so tab, and then the build step. Okay, so everybody say tab, build step, or dub step if you want, but build step is more accurate. Dub step. You have to wait for the drop. And there's very interesting build systems out there. CMake, for example, allows you to make your projects work across different platforms and things like that. There's Maven and Gradle. There's all sorts of interesting Ninja, Conan, VC package. CMake is sort of the industry standard these days. CMake's kind of garbage. All of them are kind of garbage, honestly. All of them kind of are. Like Conan and VC package are like package managers, but they kind of tie into this whole build process. Because what you would like is like if your code is using like the GNU multi-precision library to do big integers. It'd be really neat if when you hit make, it would detect that you don't have the package you need, the GNU multi-precision library, and it goes out to the internet, grabs it, builds it, puts the library in the right place, and then links against it. That'd be really cool, and those systems can do that. Like Maven and Gradle and CMake and stuff like that. CMake is the industry standard, basically. Just like Git is the industry standard despite its issues. And CMake is kind of an ugly... It's kind of ugly. It just is. Make is ugly, too. Like, this is a weird format. And if you guys are wondering why this was the format chosen, it's because the person who made Make did it in like an afternoon before they were going on vacation to Mexico or something. And they're like, here you guys go. Here's a simple build system. And they kind of worked out. And so it's like, okay, well, if I need this, and it compiles this. And if I need this, and it does this. And Makefile just figures out what it needs and builds it. By the time he came back from Mexico, everyone was using it. And the syntax was fixed. Like, that's the syntax for a Makefile. And he's like, oh, if I had known this would have been popular, I would have like spent more than like 30 seconds making it. You know, same thing with JavaScript. Like, JavaScript as a language was built over a weekend. You know, the guy had no idea that he was going to, you know, have everlasting fame as a Ike, I think his name is Brandon Ike, would have everlasting fame as the founder of JavaScript. And if he had known it, he would have spent more time making it a little bit cleaner. So this is kind of relevant. Relevant XKCD. How to ensure your code lives forever. Let's not overthink it. If this code is still in use that far in the future, we'll have bigger problems. So yeah, Make was literally made like on the spot with no real thought beforehand. And didn't expect it to spread outside of IBM or wherever it was made. And so now we're using it, you know, 40 years later. Whereas if you over-engineer it, you know, you engineer it, you make it nice and pretty, then nobody ever uses it. So yeah, JavaScript is definitely over here as well. NPM Ninja is for Vim. Tab build step. Yeah. Actually, other things are easier to learn. Maybe. I mean, I can read this. You know, like But let me show you like a more complicated makefile. So you can set variables, and so here's all my compiler flags. So we're going to turn on debugging. We're going to turn on the optimizer. We're trying on link time optimization. We're going to make it generate profiling code, which probably should not be in the default makefile. We're going to do C++20, all warnings turned on, and extra warnings, which is more than all warnings. Which still isn't all of them. It's just extra, more on top of all. All is not all warnings. The compiler we're using is G++. So the nice thing about doing it this way is that all you have to do is make one change like that, and then the compiler that you use switches from G++ to Clang in all of your compilation steps. Whereas if you do it like this way, you would have to go, all right, change that to be Clang, change that to be Clang, and change that to be Clang, and change that to be Clang. And if you want it to be compiling using C++20, you do dash standard equals C++20, and you have to go to here. And, you know what I mean? It's like kind of annoying. So Makefile has a variable system, which looks like this. It's a stupid syntax. Like it doesn't like what, you know, like what's happening here is a normal reaction to this. This is basically how you make a variable. You make a variable, you say equals something, and then it just substitutes that in. So if you want to load the value of the variable, you use $sign and wrap it in parentheses. Why? Because somebody was going to Mexico in half an hour, and that's what he came up with, and we've had it ever since for 40 years. So are you going to learn how to do this in 41? You're learning it right now. This is how you make a makefile. So in the public directory, there is public/makefile. This is like a makefile for you to like look at and admire and use. It automatically compiles all .cc files together into one project. Every .cc file depends upon every header file, which is not good, because this will trigger a full recompile every time you change any header file, even in the slightest. But I didn't say it was a perfect makefile. I'm just saying it's a fairly powerful one. So you just take a bunch of .cc files, .header files, and it just figures out what to build automatically. And you can just edit the compile flags, like if you want to get rid of the profiler, you can do that. Turn off optimization. You do that. And so you just quickly switch between like, you know, optimized mode by switching the comment. The comment is of course with a hashtag, because why wouldn't it be? So, yeah. And so basically there's a sample makefile for you guys to look at, because honestly, learning how build systems work is actually really important. There's actually people, like you could get a job, Sal, at Microsoft just working on build systems. So do you write code? Not exactly. Like, are you programming Windows? Not exactly. What do? I make building Windows faster. I make it possible to compile Windows 11 in half an hour instead of 4 hours. And so when you multiply that productivity across the entire organization, it's a massive amount of time savings, right? And so there are people called build engineers that just work on making builds smarter and faster, less bug prone, you know, that kind of stuff. So my compile command is a little bit different. My compile, you can see how many different options I've commented out over the years. My compile command does have like all the CC flags. Like I use the same variable name with what warnings I use and all that kind of stuff. Yeah, I do have that, but this is actually shell scripting. So you can see I got a shebang there. Shebang, shebang, she moves, she moves. She floats like a butterfly and stings like a bee. Yeah, no Ricky Martin fans out there. Fair enough. Okay, so but that is called the shebang character there. Anything that you see starting with a shebang is shell scripting. So I have a shell script that runs multiple stages of a build. I guess, for a single source code file. And so it first runs easy peasy on it, which is my static analyzer. It then runs Google's static analyzer called CPP check. It then runs then it runs G++ on it. So there's 3 phases that it goes through. And if any of the phases fail, then the error code is set and it quits. So it does phase 1, phase 2, phase 3. So you get lots of extra checking on your code, lots of warnings, lots of static analysis done on it. So if you make common mistakes, it finds it. Because the goal is to make it easy on CSI 40 students to find their mistakes before they fall off the edge of the world. Shell script is a cybersecurity issue? Nah, not really. Shell scripting is life. Shell scripting is amazing. All right, so that is it for today. Go through the source code for complex numbers. These are all the things you're going to have to implement. Am I not in the answer directory anymore? All right, good. So you're going to have to implement like complex numbers from algebra. So you're going to use your knowledge of operators, like adding things, subtracting things, comparison, double equals, how to output, how to read from the keyboard. So we're continuing our process of learning how to make classes properly in C++. And at the end of the day, you're going to be able to just add 2 imaginary numbers together, multiply them together, add 2 complex numbers together, that kind of stuff. And you're going to have till like next week to do it sometime. Get started early. A lot of students have kind of fallen into the habit of waiting to the last minute. And then it's like 3 o'clock in the morning, the night before it's due. They're asking for help. I'm asleep. Like, it's not like, I'm dead serious. Like, you know, everybody always like poo-poos professors say start early. Yeah, you need to not wait to the last minute. Like, I would start on this assignment immediately and just do a little bit and just kind of see how it's going to go for you. And then you'll have a better estimate of like when you're going to be able to finish it. Do not start this the night before. Do not start it the day of, especially. Like, that's just begging for death. You know, like when you start at 11:30 when the assignment's due at noon, right? That's just like, what? Like, how is like STF2 half an hour before it was due? The student's like, help. Like, I couldn't do it in half an hour. You know what I mean? Like, like that's just, man. Like, you know, even the day before is like really pushing it. Like, you need to give yourself a 24-hour like window, like where you want to be done like on Thursday if it's due on Friday, and then when things go poorly for you, you've got 24 hours to like fix your mistakes and things like that. Okay. Yeah, everyone procrastinates, but in computer science, procrastination bites you hard because with an essay, you can always just, you know, here you go, you know. But in computer science, if your code doesn't compile, it's a 0. There you go. All that time and effort you put into it, you get a 0. You know, so Elden Ring time. All right. So thanks everybody, and hope you guys had fun today. I will see you guys on Friday. Peace out.